So these are the requirements for zero cross comparator. So since voltage is dropped across and FET is low, we know the RDS on is very low. It's order of 50 to 100 milliohm. So even when you apply the full load, that will be like order of 50 to 100 millivolt only. So which means we need a very high gain and low offset comparator. Okay. So I mean, you can think about like assuming 100 milliohm RDS on and 1 millivolt error if you have, that means you are off by 10 milliamp in the current. Okay. Because 100 millivolt will be the drop when you have a 1 amp current. So which means 1 millivolt 1% will correspond to 10 milliamp error. So instead of detecting the 0 current, you will be detecting minus 10 milliamp. Okay, so minus 10 milliamp is you are losing in the FET and that will reduce your efficiency. Then another thing is comparator delay. So let us say you are not able to immediately turn on the comparator. So let us say you have made your offset 0, everything 0, but there is some delay in the comparator. So until that time your inductor will be having reverse current. So then again the same problem will happen. So let us say I am operating at 1 megahertz and 10% duty cycle, which means 10% duty cycle means your duty cycle is very low. So I know my output basically the fall time of the current will be smaller, the slope will be much faster in that case at lower duty cycle. So now without so it's a 10% time you have, so very small time. Okay. So now your output discharge is what, the discharge rate? V out over L. Okay. So L is I am considering 1 micro and V out is 1.2 volt. Okay. So which means 1.2 amp per microsecond, and if you have a delay of let us say 10 nanosecond, so 10 nanosecond is nothing but 1% of your 1 microsecond period. So and 1% of 1.2 amp is nothing but 12 milliamp. So this will introduce 12 milliamp current, which means you will be certainly looking for order of 1 nanosecond or so, the delay in that. Okay. So and if you increase the frequency, you are operating in 10 megahertz. Now you can think about 1 nanosecond will cause a 10% delay. So you would be looking for order of hundreds of picosecond, very fast comparator. Okay. So the one, which means first thing you have to get rid of the offset, you have to make sure your gain of your comparator is very high. Other thing, delay should be minimized. So one thing you try to do actually, let us say after doing everything you still not able to achieve very good accuracy. So you try to compensate. Compensate means instead of detecting 0, so let us say I am seeing a 10 milliamp error. So instead of 0, I will turn it off at 10 milliamp. So it will go to 0 in that case. So that is how you compensate. But you do this at across, make sure that across PVT it is stable. Okay. I mean plus minus 10%, 20% variation will be okay, but it should not have like a 100% variation. So in that case you may not get benefit. So it has to be a bit accurate. Okay, so there are different topologies you can use. Conventional 2-stage will not be suitable mainly due to large delay. The moment you have more stages means more delay. Okay, so high speed comparator with offset cancellation is usually required to minimize the error. So most of the time we try to use current comparator, okay, or inverter based. So let us see how it works. So this is your current based 0 cross, and this is nothing but so you have a, I mean if you look at this is nothing but a current starved inverter. Okay. So instead of a PMOS switch, you have the current, high side current here, bias current, and your input is you can say is received by the, so this is a common gate, okay. So inverter is usually implemented using common source, but this is a common gate because, so now think about this, if these two currents are same, so depending upon whether bottom current is high or top current is high, it will decide your output state, whether it will be 0 or low. So now let us say this is 0, the source is 0, so both will be having exactly same conditions, okay, the same current, and the bottom current will also be same because you are mirroring the same current in the bottom. So if your mirror is perfect, then bottom will also see I bias, so you will be basically looking at a 0 level, okay. So now the moment this, if this is negative, then you are applying more VGS here, so this will become stronger, it will be pulled low. Now if it going above 0 positive, so you are reducing the VGS, making it weaker, so this current will reduce and this current is constant, so it will go high and it will detect the 0 cross, okay. And these two inverters are used to basically make it rail to rail, because this won't be rail to rail obviously because of this current, and it may be slower also in the edges, so it will make it fast trip, so it will give you a perfect 0 or 1 level, okay. But what is the problem with this? Yeah, so current matching is the main thing you require, so which means these two currents, bias current should be matched and these two devices should be matched. So you can do a very good layout, everything, but still there are chances, and we know a small mismatch here, we are looking at around 0 level may introduce large error. So you can minimize the offset with a good layout, but still there are chances, even if you do a very good layout, there are chances of mismatch. So we have some better techniques, better topologies to do the same thing. So look at this one, this is nothing but inverter, okay. So inverter can be used as comparator. Think about it, these inverters have certain threshold, so let us say VDD by 2. So if your input is more than VDD by 2, your output will be 0 if it is less than, so which means it can be used as a comparator, but around that threshold only or trip point only, you cannot use any other input, okay. So what we do actually here, so let us say we take this this phi and phi bar are generated from V gate N, but that is what we are controlling, bottom, so non overlapped clock. So when this is high, or let us say start with the low, when you are basically PWM is low, what you do, you sample it, so you take V gate N and you basically generate two output, just any switching switch cap circuit, what you do, you need phi and phi bar. So you take V gate N and generate using a non overlap clock generator, generate phi and phi bar, which are complementary phases, okay. So what you do actually during phi bar, you sample this, okay, and so this phi bar you can say it's in synchronous with your V gate N, okay, and this phi is in synchronous with V gate N, okay. So you take V gate, and but the reason we require a non overlap for any switch cap circuit, you require a non overlap clock, otherwise there will be charge sharing and your output will be completely screwed up. So let us see what is happening. So if I what happens if I connect the input and output of an inverter? So it will be biased at its common mode, or depends on the sizing, it may not be VDD by 2 exactly, it depends how you size your whatever trip point you have, so it will be biased at that. So your and this other end of the capacitor is connected to ground, so this capacitor will store the trip point of this inverter, okay. Now during phi, you turn on this switch and you start sampling VSW. Now if VSW is negative, which will be the usual case when you start, because the 0 current will happen after some time, because your current is charged during on time, and during off time it has to discharge and take some time and then cross 0. So, it will start with negative, and what will be the state of this capacitor, other or plate of the capacitor? Trip point plus your input, which is negative here. So, this will be below trip point. So, if it is below trip point, this will be low, okay, because we have another inverter here. So, this will be high, this will be low. Now, the moment it goes positive, this will go above trip point and this will go high, okay. So, that is how you use inverter as a comparator. Now, this, which means now you can use, by doing this you can use for any input voltage. So, this will act as a comparator.
Here we said that we were applying logic for making the comparator work only.
Yes, so this will control now your, this ZXD is nothing but is controlling your gate driver. So, this ZXD is this. So, this comparator is replaced by this thing or this 0 cross data. Okay. So, all you are looking for this ZXD out to turn off your NMOS. Okay.
So the 5 signal and BJT signal both should be same, or just
Which one? 5 and?
5 and BJT should they be the same signal?
Yeah, you can, no, not the same signal, but all you have to make sure it's a non-overlap clock. Na? So, if V gate N and V gate P know it's a non-overlap, then you can use the same signal. That's not a problem. Okay. But the only thing is V gate P is low. So, what we are doing here, when you are turning on this, you are not sampling that, this sampling you are, so the phi bar is actually in synchronous with V gate P, not the phi, because we want to sample VSW and detect the 0 cross during the discharge. So, which means the VSW is low at that time, not the high. When its VSW is high, that time you store the trip point of this inverter across the capacitor. Okay. So, but there is a problem with this. So, let us say I have sampled in this capacitor I have sampled the trip point of the inverter, and when I am sampling my VDD is slightly changed. That is quite possible, VDD is not very stable. So, even if it is, let us say, change by 10 millivolt, 20 millivolt during that time. So, you have sampled some other trip point, now your trip point is changed due to change in the VDD, and you will get the wrong signal. So, then again it will introduce the error, and 10 millivolt is a huge, 1 millivolt we looked at, it is causing 10% error. Here 10 millivolt will be like 10 times of that. Okay. So, we cannot afford to have large error, we know, and that is why this will not again work, because it is sensitive to VDD. So, what can we do? How can I make it insensitive to VDD?
You can use the regulated output as its VDD.
No, then you need a whole regulator. Just do the small thing, I do not want to put a big regulator there.
Its output also.
No, think about this. Is it sensitive to VDD or not?
No, not sensitive.
So, just replace the inverter with this.
Ideal current. But making the current source itself is a MOSFET.
Sorry?
Making the current source
Huh?
itself is MOSFET.
So, what is the problem with that?
There will be like DST change.
Huh?
If a
He's
DST
talking
changes,
about on RDS.
No, how, I don't understand.
current source itself is a MOSFET.
As long as current is a constant, do you think your current will change every cycle? In 1 microsecond your current will change? Why I mean, tell me the reason the current will change so fast.
Suppose source voltages are being,
Uh-huh.
so your source voltage is changing.
Uh-huh.
So the formula I.
No, that means you don't know how to mirror it actually. When you mirror, your gate follows the source. So, VGS change remains 0 actually. Otherwise, your mirror, that means the mirror you have designed is very bad. Okay, because you have you mirror from a diode connected. So, when you change the source, your drain will follow that, and drain is connected to gate. So, VGS change will be 0 when the VDD changes. That is how the current mirror works. Otherwise, no current mirror will work in that case. Okay. So, the only sensitivity will be through your RDS, and since it is saturation, RDS will be much larger. So, and that is why for most of the current mirror we use a very large channel length, not a small, to basically reduce the channel length modulation, or you can use a cascode also, and if you use a cascode, then you can make it even better. Okay, so you can design a very good current source, that is not a problem, and you can make it very insensitive to VDD. So, I have simply replaced these two inverters with this. Okay, and now what will happen? When you are sampling this, you connect in a diode connected manner, and when you basically when you are sampling the trip point of this inverter, and when you are sampling the input or VSW, you just open this switch, and depending upon the voltage on the gate, it will decide. So, if it is a positive, then it will become stronger. Okay. So, it will make it 0. No, this there is a drawing, this drawing is incorrect, this should be NMOS. Okay. So, anyway, I will fix this. So, you can assume this is NMOS, not a PMOS. And then we need one more inverter, because this is ZX out bar. If you compare with this, we have a 2 inverters here, we have 1, 2, 3 inverters here. Okay, so this is, I don't know if the pen will work. So this is, which one?
Gate to source.
No, but we are, no, we don't mean to be to have a source follower here. Why do we need a source follower? Input impedance is very, so there is no, I mean you are not driving any load as such here. So why do you need a source follower? And this is NMOS. Okay. So which means if I have one more inverter, then I will get okay. So the reason I am having this one more stage, I could have put the, you can use a inverter directly at the output, but in order to just match the threshold, I am putting here, so that you basically trip this at, and then again apply these two inverters to get rail to rail output. Okay. So these are like some techniques to design zero cross detect comparator. So, but these are not the only techniques. I mean, you can, if you know any other topologies which can work with a very low offset and high speed, then you can use that. You are not always forced to use these kind of circuits. Okay, but this is simpler, and the another advantage is I mean delay is minimized here, because number of transistors are not that many. If you look, like in an inverter, you have only 2 inverters, 2 transistors here, simple. Now think about if you are even using a 2-stage comparator, how many transistors you will have, and every transistor will have its parasitic capacitance and increase your delay. So it will minimize your delay. So this is the most important part of your DCM operation, the zero cross detect, and you can use this output to decide when to enter the DCM. Okay, or in fact you can use this to enter into PFM or pulse skip mode also. Okay. So if let us say you decide to enter the PFM mode right away when you enter the DCM, then you can use this output. So there could be different ways of to how to enter the PFM mode. One is like you can monitor the load current, okay, and you can decide what is the load current. So, but one thing you have to make sure that you have to always monitor the minimum duty cycle. Okay, so if your minimum duty cycle occurs before your whatever the threshold for the load current you have defined, then you have to enter, you are forced to enter, otherwise you cannot regulate the output. Okay, sometimes you use both, like combine the two and use that. So you can take this 0 Zx out, okay, and if the moment you get Zx out, then you can decide, okay, this is the time I can enter into PFM mode. So in that case you don't need information from the current, okay, but if you know this is the current, minimum current I want to enter in the PFM mode, and you know that you will always be operating at that current in the DCM, then you can use the current information. Or then the third thing, you can use the D min. The moment you saturate the duty cycle, you just enter the PFM mode. Okay, but this is the basically you have to analyze which is the best in terms of efficiency. Whether you want to wait until you hit the minimum duty cycle, or you want to enter the PFM a bit early. Because it's quite possible that when you hit the D min, your load would have dropped to very low current and your switching losses may start dominating. So, in that case you want to enter the PFM mode a bit early and start reducing the switching frequency to improve the efficiency. So, this is simple implementation I have to show you that. So, this is my 0 cross, okay. Then after that I have a high edge detector and then flip flop, and this is a SR latch actually, not the same D flip flop. As I told you, there could be different ways of implementing that. And then I have a high Z input here which disables the power FET. Okay. So, let me remove this. So, one thing I wanted to show you guys. So, there are some parasitic capacitance at this node, because this is connecting the drain of the two devices. So, it will have some parasitic capacitance. So, I am putting a 1 picofarad here. So, what would happen when we when I high Z means put this node at high Z, what would happen? It will start.
The current will start flowing.
Yeah, current will start flowing, but what will it? You have a L and C network here, huh? So any LC network will have a resonance. Okay. If you don't have this cap, then it will not resonate. But the moment you connect a capacitor with the inductor, it has to resonate. Okay, and we know that the DCR of this is not that high, so Q will be very high. So it will, you will see a lot of ringing there. Okay, so that may cause some EMI issues. So I'll just show you. So probe. So this is my current, and you can see it is stopping at 0. Huh? So which means my 0 cross comparator is working fine. Now let us look at the output. See. So this, I mean, your output, so your VSW node has to return to the output voltage because it is a high Z. But before it returns to the, settles to the output voltage, which is 2 volt here, okay, it is ringing a lot here. Okay. So how can I fix this? Can I get rid of this somehow? By the way, why does this ringing, why do these LC networks resonate? If intuitively you want to explain to anybody, don't tell that it has a poles on this J omega and all those.
Energy is getting converted.
So energy is stored there, okay, and which means the current direction is changed, and we know that as long as inductor maintains the voltage difference, the current will start flowing. So, it is doing nothing but reversal of. So, when the current gets reversed, this voltage, and it is a high Z node, so it will try to charge very high. Okay, when it charges, the inductor will, current will get forward, okay, and then it will try to discharge this node, then again the current will try to get reversed. Okay, so that's what happens actually. Charging and discharging of this node will keep happening until your whole energy is dissipated and the voltage across inductor goes to 0. So, if I know that when the inductor voltage across the inductor goes 0, the energy will be 0 and it will not resonate. So, I can simply force the voltage across the inductor 0. If I connect this switch in parallel to this, it will do the same thing. So, the moment I detect the 0 cross, I will turn off this FET, and to avoid the ringing I will turn on this switch also. So, it will short the two ends of the inductor and you will fully discharge the inductor actually. So, now let us see, I have just connected this and resimulate it and see if that ringing goes away. By the way, this is called freewheeling switch. The name for this particular switch is, see, very clean output, no ringing. Your output is settled to 2.5. Don't think that it was 2 volt in the previous case, because your output is not settled. You are operating in the DCM and it will take very long time to settle output. So, my output is still not settled. So, I am looking at a different time instances, that is why. See, it is still rising. So, there in the previous case I was looking somewhere here, and in this case I am looking here, that is why. So, it will take very long time to settle the output in DCM.
How do you implement that logic with the immediate,
Which logic?
that the freewheeling, that this logic is?
No, this is during high Z and PWM. So, we know when PWM is low and high Z is also high. So, that is why I am using PWM bar here actually, which means PWM is low means PWM bar is high and high Z is high, both are high, 1 and it will force this to turn on, that is it. Okay. And if the logic, the way you have implemented the logic, if a high Z only remains high during the off time, then you can simply use that, directly use that here. Then you do not need to get the PWM signal. Okay. But if there is any chance of getting high Z high when PWM is low, then it will mistrigger and screw up everything. That is why it is always to have a protection here. Make sure that you turn on this switch only during off time and also when high Z is triggered. Okay, but is there any drawback of having this? So, benefit, for noise sensitive application obviously is very critical. I mean, it may cause EMI. It may cause even radiated EMI, because ringing for high frequency, I mean the antenna loop and all those, it may start radiating actually. So, for RF application and all those, it is very bad. Even though it will not appear at the output, because it is a very high frequency ringing and this LC will completely filter out that. Okay. So, you may not see that at the output, but this node you have traces and all those which may behave like an antenna and radiate energy. So, that may cause EMI issues.
Sir, we turn off the bottom FET when the inductor current is 0. Right?
Sorry?
Bottom FET is turned off when the current goes 0.
Yeah.
So, where is the energy stored here?
Energy stored means?
We are freewheeling the inductor because some energy is stored in the inductor. That's what we are assuming.
No, that time you are crossing 0. So, when you are crossing 0 means, no, what you are saying that where this energy is coming from, but you are not exactly getting at a 0. If you get a right at 0 and this inductor has stored the current, I mean just like a capacitor stores the voltage, So the capacitor voltage cannot change instantaneously, inductor current also cannot change instantaneously. Even though you turn off, inductor will try to
Have the current.
store the current because the current storage device. It is not that if you turn off at 0 and the inductor current will fall to 0, that is not possible, because inductor always stores the current, just like a capacitor stores the voltage. Okay, the same thing happening here also. When you make it high Z, this current will not change instantaneously unless you discharge the inductor fully by forcing the 2 voltage. So, and that is what happens. I mean, inductor has stored the current here, and even though you turn off this, so that current has to be dissipated somewhere, and that is dissipating in this parasitic cap and causing the resonance. Okay. So, and that is why this voltage goes high, and when this voltage goes high, then the voltage across the inductor goes positive and it will try to get the reverse current, and then when the current flows in this direction, this voltage again will try to go to negative. Okay. And so, who will limit this voltage? This can go anywhere, it is a high Z, it may go even kilovolt. So, who will limit the voltage, positive and negative?
Output voltage.
Output voltage? How come output voltage? These diodes, body diodes, if this goes below minus 0.7, this diode will conduct, and if this goes above VDD plus 0.7, this diode will conduct. So, they will limit the voltage, otherwise it can go anywhere. If this diode are not their body diode, then it will kill your circuit actually. This is a high Z and it may go anywhere actually, 100 volt, kilovolt, you do not know. So, this diode will protect that node itself, they will clamp that to between minus 0.7 to VDD plus 0.7. Okay. So, this you have to always remember that capacitor is a voltage storage device and inductor is a current storage device. Okay. Even if you release the inductor, it will store, just like a spring, you stretch and release it, it will keep doing this and then before it stops actually, unless you apply any external force, and that is what happening here. You leave it high Z and this switch is nothing but like an external force, you try to stop that spring, that is it, at its position. Okay.